Hello, folks. We're going to be doing a bit of programming today. This is the third video in a sequence where we've been building up a differential data flow program that addresses two queries that we've been working with that deal with some social network, social media sorts of data and respond to changes in that data. Today, the plan is to, in a sense, tidy it up a little bit, but work a bit more with differential data flow to try to show off, in some cases some features, but also just what programs look like that might be a bit more idiomatic or a bit tidier. We are, you might have noticed, on a different computer. This is my laptop. Today is Saturday. That means it's jackhammering day at work. So that just wasn't going to happen. Tests indicate that the audio is totally sweet here. First of all, it's quieter. So even though it isn't some fancy microphone, it sounded pretty all right to me. We'll see. I'll record stuff and then you decide. So here we are. This is main.rs, the program that we've been working with. I have been playing around with a little bit, doing some compilations. There's a few things that I'd like to tidy up, though. One of them is, you might notice here up at the top, we have a whole bunch of types that we've defined. And type in Rust does not actually create a new type, it's just an alias. And that means that a person in submission, although they claim to be their own type, they're basically just aliases for usize, and in our computation, we might accidentally join together a person identifier with a submission identifier, and that'd be a big mistake, and we would love to have Rust yell at us. It won't happen in this context, but one way that we can make this happen is by taking our fairly monolithic computation, which just inlines, this is query 1, it's not small, and then there's query 2, it's also a whole bunch of stuff. We could make these into methods. And when we make them into methods, we can specify some generic type parameters, which will let us say, however we want to represent comment identifiers, some generic type, and then use that in the scope of our computation. And Rust will type check this and make sure that we only try to equate the equatable things like comment identifiers with themselves, as opposed to accidentally equating them with some other types. And this will be handy. This will give us a bit more confidence that we have correctly implemented our logic. And it also just shows us, it makes things a bit more tidy. It shows you what we need to do to make a method that talks about differential data flow computations. And we'll see that it's a bit wordier in some places. There's a lot of very helpful type inference stuff that Rust has done. For example, in determining the type of query, we're going to need to write down this type, unfortunately, and it's going to be a bit more gross than not writing down the type, because that's super easy. But Rust is very much about explicitness, so doing these things explicitly will make things more clear for us and more clear for other people who might show up and say, what's going on here? What the heck is a query? So we're going to do that. Let's take a swing at that. My plan is to, for both query 1 and eventually for query 2, we're just going to grab this code here, and we're going to go turn it into a method down at the bottom of our program, which is a ways away. I'm just going to collapse these things down so that we can surf around a bit more easily. We've got some of these helpful methods that converted our input lines of text into these make pretend types that we have. But let's actually write down method fun query 1. And query 1 is going to take some arguments. We'll figure out what those are in a second. It's going to take some generic type parameters, figure out what those are, some arguments, and it's going to return a type, an option. And I believe it's going to be in our ranged, and we'll type through what that means. Implement the logic for query 1. Return a trace of the results. Great. There are better comments to write, of course, and we could write little tests for this if we want to also, but we're not going to do that. So we splat down all of this code. The first thing to do isn't actually to write the code, probably. The first thing to do is going to be to write some of these generic type parameters and some of the input arguments. Let me write the inputs first, and we'll see what we actually depend on here. So we're going to need I believe, 3 collections coming in, and if that's wrong, we will fix it as we go. But I believe we're going to need some comments, which are going to be collection, differential data flow collection. Collections have 2 generic arguments: the scope in which they exist, sort of the data flow canvas in which they're currently described, and the type of the data. There's actually a 3rd parameter, but we're not going to get into that, which is the monoid that they use to describe change. That's a super interesting thing, but not on the menu for right now. Likes, collection, g, like, and we're going to need our probe handle, because our query not only does some computations, but it also registers, in a sense, a probe in the computation so that we can see how much progress it's made. Probe handle. And that's going to depend on G's timestamp, not on G itself. So G is data flow scope, or G comes from graph. That this is a data flow graph we're building, and so this is the certain current graph in which these collections exist, and for which we're going to try to probe some timestamp. So let's write down these generic arguments up here. G, com, post, and like, I think are the 4 parameters that we're going to need. I'm going to have to look up the arguments for this return type here. It's sort of gross and messy, and it's not as tidy as it could be. There's some type constraints here that we're going to want. So G is going to need to be a scope. This is a timely data flow scope. G's timestamp is going to need to implement lattice, which is a differential data flow constraint on the timestamp, which more or less means that this timestamp makes a little bit of sense and we can do all of our differential data flow mathematics with respect to it. A lattice is just it's a partial order that supports things like least upper bound of pairs or sets of elements and greatest lower bound. These operators are important for differential data flow. And we're going to have some more constraints. We'll sort of discover them as we go, but things like com should implement probably this trait called exchange data. Post should also probably implement it. And like should implement exchange data. This is a trait in differential data flow that allows us to determine hash values of these things, to shuffle them around between workers. It involves make sure that we have some way to serialize this data. So these things are important if we want to turn on a computation and shuttle this data around between workers. If we compile this, we'll almost certainly get yelled at about these traits not properly being in scope yet. That's fine. But let's try that. If we save this and cargo check. All right, we've got a bunch of errors now. Scope doesn't exist. Let's grab the scope trait. Lattice doesn't exist either. Let's start plopping these in here. Yeah, this screen real estate thing is definitely a bit more awkward. I typically, when I develop on my laptop, use these sort of virtual desktop-y type things, which works great for me, but I'm guessing is pretty terrible and nauseating for people trying to watch from home and follow along. So I'm just grabbing and dropping in these traits that we believe for these general types and traits that we're using, and for which Rust is correctly realizing that it has no idea what we're talking about. Let's try it again. What a mess. So, okay, it's now gotten down into the body of the method and is starting to complain about things like, how do we know you can hash these things? And if you recall from a few videos ago, we had a trait that let us do that. This type, okay, so excellent. We're now at a point where we are using things like our com trait, which said I'm a comment, and are trying to announce that it has 6 fields, and I'll look at the 5th one of them. What a mess. And we're going to need to deal with that. So, let's think. I mean, one thing that we're sort of conflating here, or at least we're changing from before, is we're trying to write something that's generic in like, oh, this is an entire comment, as opposed to a comment identifier, which is actually what we were sort of using some of those types up above to describe. So we might say, rather than com, this might be submission. And rather than like, we might have person. At which point, com would actually be whatever that triple was we had up above. Let's quickly grab these things, and we'll just reproduce them down here so that we can steal from them, and then we'll delete them in just a moment. So in this case, a comment would actually be all of this jazz. And I guess maybe we say date also. We could commit to dates being something specific, like integers if we wanted to. We can't, unfortunately, actually use chronos date time because it doesn't implement several of the traits that we require in order to be able to do dataflow computation on them. We could write a wrapper for chrono, blah, blah, blah. It's a bit, Rust's coherence rules that prevent me from implementing other people's traits on types that I haven't defined. It's occasionally annoying, but it's also kind of important. So, this was, let's change these things to be person date. And really what's going on here is we made the mistake, I think, of thinking that we could describe generally what a comment was. And to do that, we'd have to talk about the fact that comments are things that have identifiers and dates, and they have persons and all these weird properties of the type, where maybe we're just better off saying, no, it's a 6 tuple, but each of the fields in that 6 tuple are potentially different. So let's try this again. I wonder if this is going to look a little bit better over here on the side. And maybe I make the font a little bit smaller for all of you. So if we go and cargo check, we have distinct. So these folks need to be in addition to exchange data if we want them to instead hash. If we want to be able to hash them. Oh, was I wrong about that? That wasn't actually the problem, maybe? Let's see. So I'm going to bring some traits into scope here. I'm actually going to put these inside the method here rather than outside, just so that to see if that keeps things tidier. It's going to mean that we're going to have to reintroduce these things in our second method, but join. Okay, so we're going to have a sequence of these sorts of complaints coming out of Rust, and that's fine. It'd be great if it could just sort of run ahead and but type preference, I guess, gets in the way there. Reduce. Arrange by self. That's the thing that gets us our arrangement. Yeah, we don't have display implemented, so we will deal with that. My guess is the way we're going to deal with that is to not actually make a collection of strings as a result, but rather a collection of triples. if you recall, our output is to produce the top 3 of these. In this case, what is query 1 is the top 3 posts, the most exciting posts. So, rather than actually try to format them up, we'll just return the triples, and we'll let the person who is looking at these things and printing the output actually format them up properly. Seems like a better place to do it than in the data flow itself. So let's not do that. So instead of a string, when we're doing a reduction, let's make it be a vec. Okay. There's a serious problem with having multiple keyboards that you work with. Try to touch type one. So rather than formatting some strings, we're going to do results.push of the post. And then output is going to get the results. And that should tidy up complaints about formatting at least. Oops. Guess not. So this looks like we have some imbalanced parens here. Found submission. Okay, so this needs to be cloned. I think. Probably the same. If you recall previously, we ate some technical debt where we just said, what's going on? Sorry. Where we said, oh, we know these are integers, that's fine. We can just dereference them, and that will automatically copy stuff, which was true at the time, but now we have a fairly generic type submission. Who knows if that's, that could be a string, it could be an integer. Maybe we can clone it. Maybe we can just dereference it and copy it using the copy trait. Maybe we can't if it's a string. We don't know at this point because it's just a generic type. It happens to implement exchange data. Exchange data requires the clone trait, so we know that we're able to clone it, but Rust is telling us, oh, you better explicitly clone it, actually, because I need you to do that. So let's look into this arranged thing now. This is going to be exciting for all y'all. We get to go see what sort of horror exists. I'm going to crack open Sublime so that we can surf over to the differential repo here and look for more information about that. So we are here and looking for arrangements. And when we look for the arrange by self method, which I happen to know is at the very bottom of this fairly massive file, arrange by self is going to give us back two things. It's giving us back an arranged, two things, whatever. It's going to give us back an arranged. We only wanted the trace field, though, in it. And an arranged is a struct just up here. Pretty sure. Come on. Is that the top? Sorry. It has a stream in it, which contains sort of the data that are moving around, and it's got a trace. That trace has type equal to the second type parameter. So if we go and say, what does arrange by self give us? Arrange by self gives us an arranged, and the thing that we're actually going to get is this. So it says trace agent. This is a thing that mediates access to the trace, so that if you want to hold on to a copy of it or clone it a few times and hand it out to some friends, it's able to understand what have you done. And then whatever the default key trace is, we'll discover that, but we might even just be able to use the default key trace if that's publicly exported from here. So let's just say that we're using that, and let's let Rust let's complain our way to success here. Default key trace. Now we have to remember, what are we actually returning? This is, I believe, a vec of submission. right? So this is the top 3. If there are 3, we don't know there are 3, so it's not a 3 tuple. A vec whose length is at most 3. The associated timestamp will be G's timestamp, and R here, this is that monoid thing I was talking about, so I'm just going to say isize, because that's easiest. And hopefully Rust will yell at us and say, you need to go and find out trace agent and default key trace, and I will then import them. So let's see. All right, so we can just copy and paste from here, and default key trace is possibly not publicly exported. Let's go and check. Yeah, so it's actually trace implementations ord keyspine, and it's not pub use, so that alias isn't actually made visible. But that's fine. We can just throw this in over here. Use differential dataflow trace ord keyspine. What's all this about? Why do you need to know about these things? You probably shouldn't. It's a lot of differential dataflow publicly exposes the generic arguments that allow you to define a new data structure if you want. So this is something that if you showed up and said, hey, I got a new way actually to represent all of this exciting data, you could drop it in here. As long as it implements a few public traits that differential shows for you, you can manage your data your own way. And all of the rest of differential data flows surrounding superstructure will actually work just fine, assuming your implementation is correct. So that's great and cool, but it does make things a bit wordy and verbose. Cannot borrow probe as mutable, as is not declared as mutable. Okay, we already have a mute thing, so we actually only need to do probe there. We were going to try to take a mutable reference to the mutable reference, but since we had not typed mute probe, we could not do that. And it was important to have the mute ref in the argument down here before, because probe back then was in fact just a mute of probe handle. Here we've decided to make it a ref to a probe handle because we don't want to take ownership of the probe, we just want to borrow it mutable. All right, we're getting close. So hashable and collection are imported redundantly. I can't tell. So up at the top it says, no, it's already imported later on. I don't really know if that's a particularly helpful thing for it to tell us, but let's see what happens if we comment out one of these. Does it really not matter? Apparently. I have no idea. I mean, no clue what's going on. This is outside. Yeah, okay, so let's not do that, just so that we, that's probably a very sane thing to do actually, to leave it out there, but I'm just keen to have it be, as explicit as possible, and what have I screwed up? We've got our hashable thing there. I just failed to actually uncomment it. Sorry. All right, and collections redundantly imported. This is the helpful local definitions here, I guess, should be at the top of the file, so that then it's more obvious that collection, which I guess is 129. 129. Is it? That can't be right. That's line 129. Cool. Oh, I'm sorry. Yeah, sure. That was before we pasted all that crap up top. Great, and grade 1 is never used, but it compiles, right? So, like, this method is actually legit compiling. Doesn't mean it's right or anything like that, but it does mean that, for example, we haven't accidentally joined some submission identifiers with some post identifiers. But let's go and replace all of this logic with query one of, and it takes comments first. So comes, posts, likes, and then a mute ref to probe. And let's see what cargo check thinks about that. Bunch of unused imports. That's right, because I commented all this stuff, but seems like otherwise everything compiled just great. So yeah, all right. So that wasn't so bad. Right. Let's do a little bit more. So let's grab Q2, this code here, and go write a little bit of Q2. Now you can see that this is, all of this is fairly wordy. We didn't have any of that before. Now we've got it here, but it's explicit now, so that we can a bit more confidently say, great, comms is this particular type. Thank you for being clear, as opposed to just pulling out the fifth field and going all YOLO with it. So again, we're going to have some generic parameters, probably again submission person date, just guessing. We're going to have some stuff, but we'll find out in a moment. It will also return option trace agent board keys bind vec submission g timestamp and isize. Where we're going to have some constraints, probably very similar constraints. So I'm going to drop my buffer here so that I can stop stressing about that. I'm just going to steal all of these with it, but I think they're all going to be relevant. Now, what collections do we actually use down here? Does anyone remember? I'm going to have to rediscover them. So we've got comments, for sure. We've got no's, we've got likes. But I think that's it. Posts, I don't think actually get used. I mean, we have post identifiers. Oh, this is even wrong too. These I think is just the copy paste nonsense that allowed us to do our generic reduction of who has the top 3 scores by timestamp. That sounds like another great thing actually to make generic. Let's do that afterwards. But I think we just in here have comms, likes, and no's. And no's is very similar to likes, so I'm just going to copy paste this and change it. We've still got a probe because we're going to do all of our probing. And probably we still have these constraints here on submissions, persons, and dates. Well, we can just compile it and see what happens. What do you think about that? Oh, we already know, sorry, that some of these things are going to be a bit wonky. So we want to, let's just steal it again. This is something that we wouldn't have to steal if we wrote a proper generic top 3 by sort of method, which we're going to do just after this. Great. Where are we? Cargo check. Errors. Submission. Oh, okay. What if I screwed up? Yeah, okay. Great. I should have changed the. I'm just bad at typing. No method hashed. Okay, so we have some additional traits to import locally here. Now, we absolutely could have imported these a bit more publicly up top. I don't know. I kind of like having them be local because if we decide we want to move query 2 to a new file, for example, like we want to compile this once and for all, so that when we edit query 1, we don't have to rebuild it, then we take all of our assumptions with us, basically, or as many of them as we can with us. We still have all of the usings up here. So we got to you remember how much fun this was before. We're going to do it again. Get some joins, some counts. There's a legit thing to think that maybe these operators should just have these methods defined on them natively. And I think that's, at some point, if differential goes 1.0, that's the sort of thing that will probably happen because it's a bit silly for everyone to have to guess where to find all of them. But while the signatures are still in flux and the set of operators are still in flux, it feels a little bit better to have them be extension methods. So this is pretty stupid. I'm sure part of the problem here is that things break down as soon as we type inference breaks down as soon as any of these methods don't exist, and so everything just downstream from them, we can't even bother to check if methods are neat or not. So, oh right, great. So this is some examples of places where we had previously said, oh come on, they're integers, who cares? And now we need to be more explicit. So for example, here we were prepping some labels, right? We were prepping our initial collection of labels that say, for each of those likes out there, let's make sure that each user starts with the ability to use its own name as a label. But we don't know that the person type is actually copyable, so we're going to need to clone it. The second one is where Rust thinks there's a problem, but really what we're supposed to do is clone the first one so that we have the second one at hand. So if this were a string, for example, we'll do one clone here, and then just use the second copy of the string. We'll do one allocation. All right, 525 is this thing. What's going on here? Almost certainly this star should be a dot clone. We were looking through here, basically looking for the smallest label, but the label type, which happens to be person, again, isn't necessarily copyable, so that's not appropriate. And we've got the same issue with probe at the bottom where we had a mute ref coming in. We don't need to take a mute ref again. See how that looks. Great. Now we've got 62 and 63, some unused imports. I think we might have a few more in just a moment, so let's get to that where we do query 2 and this was, I think, comms knows likes with a mute reference to the probe. And then we can comment out all of this noise. Yeah, okay, so this is a very silly thing going on here. I think we should change this to be sum of this and sum up here, because these methods don't optionally return a thing, they return a thing. The option is just nonsense. It has nothing to do with anything. So this is a bit more clear about the fact that we're actually guaranteed to return a thing. There's no good path that doesn't return a thing. So we've commented out a bunch of code. We've wrapped each of these in the appropriate option. Let's see if this checks properly. And great, we've got now a bunch of unused 59. Okay, so it's gone and highlighted a bunch of these for us. That's sort of good. Trying out some of the plugins, and some of the plugins, are good, and some of them are crazy. But at the moment, that was very helpful. Cool. Well, it looked like that compiled properly, or cargo checked properly. So let's tidy this up. So this is a bit more sane now. Like, we have this input trait that we use, and it's used right here to create our collections. That was important. We've now got our first query, which might be whatever query 1 returns, or none. Likewise, query 2 might be whatever query 2 returns, or nothing in particular. And all of the assumptions about query 1, query 2, what do they require? All those things are down actually in their implementations. So that's good. Yeah. And we, as you saw, we had a few moments where we hadn't been sufficiently explicit about, with the clones and the dereferences, sufficiently explicit about how we actually got access to some of this data. We just said, oh yeah, just use it. And Rust is very clear and says, absolutely not. You must. This is a type that you must tell me how you want to get your fresh copy of it. So we did that, which is good of us. All right, what I think would be cool to do now is to go and put together this top three operation. And we could do top K actually if we wanted to, but where we come in with a collection that has this type, I suppose, post, count, and timestamp, where maybe post, maybe submission ID, maybe just totally generic. So we could do a totally generic top thing. This can also be principal, totally generic. It happens to be ordered, right? This pair, but really we didn't care about the fact that this is a pair of a count and a timestamp. So it really just needs to be something that's ordered, and that's good enough for us to go and write down some aggregation. So let's try to see what that would look like. So this is now a method that we're going to write that takes a collection as input and produces a collection as output. It is not an entire query by itself. It's a helpful subroutine. It's still going to look pretty similar, actually. So we're still going to have a fun, let's call it top K, which is going to take some arguments, some generic arguments, and some actual arguments. Probably there's going to be a G, because there's always a G. Just rule of thumb, always a G. We have now these posts, let's call them, I was going to call them K for key and then V for val. So, what is the post ID that is the things we want to surface by as the top, however many of them, and then the associated values, which are going to be the things that drive how excited we are about them, sort of help us put them in order. So we're going to have an input collection type G, probably K comma V. Just thinking that's going to work out. And we're going to produce as output a collection of G comma vec of K. Maybe we do that. I mean, we could, there could be a data parallel version of this that produced a collection just of G comma K, where the top elements were still sitting there as tuples. So there's a question of should we actually go and assemble the vector holding these results. Maybe not, actually. We will need to do that eventually for sure, but it's reasonable to think about an operator that doesn't bother to do this because we've got some downstream logic to do. I don't know. Let's just do this for the moment. We're still going to have some constraints because when you're writing generic programs, constraints are good to have. These are the things that let Rust reason about the correctness of your program without actually knowing the specific types. Unfortunately, we've got to rewrite a bunch of these timestamp implements lattice, and we will want K to implement exchange data and stood hash, and V just needs to implement, I think, exchange data. We don't look at V when we're distributing the records around in the same way that we looked at the key K. Great. So let's get to work then. All that we know at this point is that input is this collection structured thusly. So what we're going to do is take our collection and repeatedly do these sorts of input. Get this up to the middle screen here. Input.map of key comma val, and what did we want to do? We wanted to do a little hash of key dot hashed mod, and we said 100. To be honest, this is a bit silly, like we're just making these numbers up. building a massive, robust, works at any scale sort of thing is interesting, but not something we're going to try to reason through here. So we're going to hash the key, and then val comma key. We want them in reverse order so that when reduce sorts them, which it does automatically for us, it keeps things ordered as part of its strategy for canceling out positives and negatives to make sure that we see sort of the canonical representation of data. It ends up merging a bunch of sorted lists, and that's actually just handy sometimes when we want to do top K style operations. So we've mapped things. Let's reduce them now. And we don't really care about the key, which is just the hash, right? We do care about these keys and vals, but in the context of this reduction, the key is just the number 0 to 99, which is the modded down hash. Input, output. So we're writing enclosure. And what goes in here? We need to, I think, more or less steal this logic here. So we don't actually know much here about count versus post. It's fine, we didn't need to know about count versus post down here. We just needed to know about val. Where did we? Okay, so we got, this wasn't even a count. This is a pair of count and timestamp. So this is really just val key. Val key. And we don't really care what the weight is. This is, maybe we have, oh, this is too bad actually. Let's think. This is technically wrong at the moment, because if we had two copies of exactly the same key and exactly the same value, what do we do? Do they count against our k, right? So we took, oh, we forgot to limit use size. We don't need another thing called k, though the top k is usually, top k is a thing. We don't get to change k to be top limit or some junk like that. Maybe we'll just, sorry, limit, yeah, cool. There might be some, anyhow, we'll see. If we had multiple exactly the same keys and values, so that weight was now like 3 or something, this sort of does a distinct as part of its action. Let's just document that and go with it now. So returns the top limit distinct elements in input by value. Keys in input by value. All right. So all that this is doing is thinning down the data sort of in these batches of 100. We walk through and say for each batch, for each bucket, just keep the top limit, and away we go. We could also, we could write a more interesting loop here that says, while limit greater than 0, keep walking backwards through our list, push, the min of remaining limit, comma, weight. That's a good idea, but I don't really want to do it at the moment. All right, and we need to do the same thing now, second time, where we don't use any more hashing, and we could, if we wanted to, we could. This is one of the cool things. This should all approximately just work. So this is our top K, and we were supposed to go and collect everything. So maybe we have this last thing do an accumulation for us. Maybe we just kind of ignore it. What to do? The whingy problem here, sorry, is that these have this nice elegant symmetry with we're taking a collection, we're returning a collection of the same type, so we can just chain all of them together. And the very last thing that we're going to do is glom them all together into a vector. I suppose we just do that. So we're going to return top a dot reduce dot. Okay, no, it's still got the key of the empty set. So we can just again do reduce input, output. We can almost just do result dot extend input dot iter. So these are all references inside. So we need to actually they are pairs of what at the moment? Vowels and keys, weights, and we want it to produce as output. Or sorry, not produce as output. We want to stash into the to the result vector. And apparently I've should close the map, should close the extend, and now output dot push result, 1. So now we have a vec of the top 3 things there. In the wrong order, actually. So let me change that. Sorry. So there. Now they're the top 3 things by this value. And in principle, actually, we can just let's see if this is correct. All right, we actually have a few other issues here because the data that come in are initially key value, but they're not key value here. They have some hash in front of them that we're just going to ignore because we actually, if we wanted to, we could just do that. Isn't this clever? So this takes the same hash that we had before and just says, great, let's thin you down a bit more. We could map this down. I was going to say hash mod 1, but it's kind of silly. But we do need to tidy up that value. So dot map hash we are saying, sorry, just to be clear, we're producing output. Okay, we're swinging these things around. This is going to cause problems. So let's be clear about it. Let's produce keys and vowels, and each time we go around, okay, we're going to swing the 2 around. Maybe we would be smarter at just having everything be so let's let input map key comma val. Basically, we're gonna think about everywhere wandering around with key dot hashed val comma key. So this is the sort of the type. There's a hash value, and there's a val and a key that we're going to float around everywhere. So when we get this data in, hash val key, we're going to do hash mod whatever val comma key, and we're going to produce val comma key. In our output, we will occasionally val comma key, reduce down the hash, and just do this all over the place, and let this be a 0, though that's very silly. But it leaves us in a situation where we can just call our reduce function here. It's not let's call it 0, even though who really knows? I mean, we know, but and we're not actually returning a thing yet, so let's I think this is the right type to return. Okay, let's see what this. Open some crazy. Yeah, no one loves you. Go away. This file contains unclosed delimiter. I believe that. Yeah, well, nothing else, we need a semicolon. We need some of these traits again. So hashable, for example, unclosed limiter, the 507. This thing is badly closed down here because, yeah, what a mess. We didn't bother to actually close off our reduce method. All right, cargo check again. Okay, I'm just bad at this apparently. No method named reduce, so okay, we're back into this business. La-dee-dee. La-dee-dee-dee-dee. Check mismatched types. Expected struct found tuple. So, oh yeah, okay, this makes sense. So the thing that comes out of a reduce is a pair of the key and its values, so we want to tidy this up with hash comma vec goes to vec, because we don't actually care about the value 0 in front of this thing. You know, we could leave it there, but it's polite to tidy it up. And this is good. There's a few moments here where we totally ignore some things. We should acknowledge that. So 539. We don't really care about val. We don't really care about weight. This is just, you know, they've been put in order, and we just want to read the key out. Absolutely, we want to dispose of the hash. Here, we don't really care about the hash either. We could say, I wonder if I'll just write this down because it's for mathematical symmetry, and let's hope that Rust will provide, or LLVM, I suppose, is actually what's helping us here. All right, there is some stuff going on in 522. Interesting. So we're doing val.clone, key.clone. My guess is that it is having a difficult time determining that we're trying to push not the references to things, but the clones of the things themselves. Is that right? No, that's totally wrong. I'm just making it up. I'm full of it. It figures all that stuff out magically. Rather, the problem is that limit, which is a use size, Rust got a little confused and thought, hey, maybe you mean to take a reference to that. And if you were to do that, it's not clearly going to be around forever. But that's fine. We fix that. All right. So we're going to replace some stuff now. All right, we're going to go and here's the moment where we started hashing things, and here's where we're doing all of our pushing of things, and we made the vex and so. So let's hop in at this moment and think about applying the limit function. And to apply the limit function, we need to start with something which has type key val, which apparently we have that. So let's score, because this is, you know, comments and scores, and then we'll put the arrangement logic. That arrangement equals limit of comment score, comma 3, and it produces this vec stuff. So we should just be able to do that, I think. Oops, that's not over here. Unused variable. Oh, holy crap! Is there seriously a? We already had a comment. Okay. Let's. That was a near miss. Thank you, Rust, for telling us this went unused. That would have been a logical bug that might have taken us a while to figure out. All right, this compiles. So I'm just going to garbage collect that. Not really sure the right way to format all of this stuff. Maybe we'll just put it in one line. But we can also do this back here, where we had posts, counts, and timestamps. So we're gonna do the same sort of thing. We're gonna reuse the name this time. Post score equals post and now we can let arrangement equal post score dot arrange by limit of post score comma 3 dot arrange by self. Ta-da! And see if that works. Cool, we've got some things we can imports we can get rid of, apparently 363. So this is again, moving things out of the this particular method didn't need to know about apparently hashable or reduce once we've wrapped up limit somewhere else. Now we have, I hope, made this a bit more clear at the same time, though we'll take a breath in just a moment and scan through just to see if that's actually the case. I'm just going to format some things a little bit better because surprisingly that actually helps with clarity also, for me at least. What was the other one? Oh, we'll need to get some new line numbers. 413. All right. 413. Oh, we could just look for the green lines because that's actually a thing. All right. This probably is nice and clean. Let's start up a cargo build. This slightly awkwardly, it takes about 3 minutes or so. Some good things might happen though. So one of the things we've done, for example, this limit method is, it's technically generic with respect to k and v and stuff like that. But we use it twice, and we use it twice with the same type parameters, with submission as the key, and the value is a pair of, I think, an I size and a date. And because they're exactly the same thing, I'm hoping that what will actually happen is that Rust and LLVM will compile this once rather than twice when we had it manually inlined both times. That time I think it almost certainly would have code gen both of them and then look possibly for some code deduplication. But yeah, so we're now with, I would say, slightly more terse code. So it probably isn't fewer lines of code in total, but it's a bit more compartmentalized. So like when we look at what's going on in query 1, we can sort of kind of walk through. Okay, here's some liked comments. Actually, let's suppress this for a moment. Let's talk through this. Let's talk through all of our code and try to make sure that we believe that it's properly idiomatic. So we've got liked comments, and what this is supposed to do is give us back submission identifiers that were liked by people with a multiplicity that corresponds to the number of times that they were liked. Delete something so we don't need them anymore. So that involved taking the set of all likes, calling distinct on it, just to make sure that remove duplicate likes, maybe not necessary. So we're going to remove duplicate likes, even though we don't know if duplicate likes exist or even what the intent really was, but we're going to do it because we're amazing. We map down our likes, which have a user and a comment, just to the comment identifier. We no longer care who the user is, and in fact, we'd like to get rid of that information so that this collection can be consolidated in place. So that if a comment is liked 27 times, we don't have the list of the users who liked it. We just have the comment and 27. And okay, and we join now with our collection of comments to get out the post identifier. So we don't really care about the comment. We want these things by post. And a join and then a map handles that for us. There is a more terse way that we could have done this with a method called join map, which fuses these two together and doesn't cause us to materialize the slightly larger tuples that result from join, but we don't need to worry about that. comments are then this, and post scores become the scores from likes concatenated with the scores just from the comments themselves, and skip the consolidation. The consolidation is important typically if you're about to inspect the results, but almost all operators, like count, for example, where post score is about to go, almost all of these operators will first effectively consolidate the input. They apply the same logic as consolidation. So we don't actually need to put consolidation in place there unless we're going to tap into the stream itself and watch the physical tuples flowing past, which I'm not doing. Great. So this is good. We could, if we wanted to, you sort of see here that we describe this is the post score, and then we just do a bit more work with post score after it. We concatenate in the post identifiers themselves so that these even absent posts, or posts with no scores, get at least some representation. But we could, if we wanted to, we could sort of start to streamline all of this like that. And it's up to you, I suppose, whether this is more readable or not. It's a legit thing to wonder. We could, for example, possibly make it a bit more idiomatic isn't exactly right, but like if we start with the post identifiers themselves and then concat in the two other places that scores come from, which is liked comments and the comments themselves. This is something we could in principle document as ensure all posts get a score, not scare. Likes contribute to posts, comments contribute to posts, and this stuff down here is now just getting the count out and subtracting 1 from it. And then we join with the posts to get their timestamps. Yeah, I'm not actually sure this is clearer for any of you, but it helps me. And yeah, like a lot of what's going on here, computationally, what's going on here isn't too exciting. I mean, it's some joins. There's this distinct. This is some interesting computation. There's some state involved there. There's this join. That's going to index both of its inputs. The maps are streaming operators. They don't maintain state. Explode is a streaming operator. Map, concat, all these things are streaming operators. Count is going to go and do some stateful stuff. There's one opportunity for optimization that I can see here, which is kind of interesting and might be worth doing. Let's finish this and we'll talk about it. But the gist is roughly that count is going to produce this data post, count. But it actually produces an indexed arrangement for us. So it produces something that is indexed by post and keeps the count. We're going through and subtracting 1 from it. But we could totally just do the join with the unsubtracted count using the indexed representation that comes out of count. And that saves us essentially maintaining another copy of data indexed by post, both in the output to count and in the input to join. So we would cut down on the amount of work we do, the amount of memory we use, that sort of thing. So I'm going to leave a note here. Fuse, count, and join with arrangements. This is a really cool thing that you can do in differential data flow. I like it quite a lot. But yeah, it probably won't actually make things appreciably faster. It could, in that the state is proportional, because we have all of these posts present, proportional to the number of posts. That actually is a thing that grows quite large. But but there's lots of stuff going on here, and removing one of them may not fundamentally change the performance. We will see. All right. We have no idea what's going on in here. I mean, sorry, we wrote the code, but like at this point, we have no idea if this is actually something we could optimize. We don't have a lot of transparency into it. That's fine. We could, in principle, look into limit and see would it have helped to have the data arranged in a particular form? But since we're and it could go hash things up right away and shuffle data around into buckets, I think the answer is no. All right, let's look at query 2 now. Query 2, we might have a little less flexibility about because it just gets right to work and doesn't reuse too many collections. But if you recall, this is a computation that does this label propagation on a graph of who knows whom. So we have this knows relationship, which has pairs of persons. And the gist is that we're going to take some likes. People like certain submissions, and we're going to circulate that information around on this graph. And everyone who likes the submission is going to try to keep track of the lowest person identifier they've heard of who likes that submission, where we forcibly suppress information about submissions people don't like. This is just going to make sure that on the connected component of people who liked a submission, this information flows, but it stops at the boundaries of that connected component. So we don't send information about a submission across an edge where the people on the endpoints don't both like that submission. Woof. So I think I just, in the first video, just wrote this and typed it and didn't really explain a lot, which is too bad. So let's talk through it just a little bit. We're going to produce the sort of final labeling, which describes the connected component structure. It's going to have people submissions. This is the graph node, the circulated label, and the submission with respect to which we're circulating labels. Those don't visually seem lined up anymore. I'm not sure exactly what happened, but tidied it up. Maybe the right thing to do would have been to describe a label type that just happens to be equivalent to person. Though this is fine. So we took likes. We needed to create some initial likes to get things going. Yeah, you want to see a fun trick? This is also correct. Ready? Get ready. We need to do that just to make sure the type lines up properly, but ta-da! If we throw away all the data, this is also correct. Why is it also correct, you might ask? It turns out that it doesn't really matter in this computation where we start from, because under some constraints. We can start from the empty collection, because in our iterative computation we're going to repeatedly reintroduce the base labeling defined by the set of likes. So even if we start with the empty collection, at the end of the first round, we will introduce all of these base likes, and then the second iteration will be essentially as if we were just doing the first iteration. So really, this isn't. This was letting us sort of jumpstart one iteration in our computation, but not any faster than it would have been any other way. So we can actually, if we want, we can just throw away all this data. And this actually saves us a bit of work because there's some clunky logic associated with the initial value of the data that come in. We have to sort of process that a few times. So we just throw it away. If this is weird to you, then feel free to take a moment and sit down and sort of pencil through. What is the initial value of labels? Oh, it's empty. Okay, interesting. What is the second value of labels if we work through all this logic? It's basically empty all the way down to this point. But then we concatenate in this likes labeling. Basically, this is our initial labeling second time. So what's going on in here? We take our labels, which are a node, label, and comment, and we're going to touchpad is excitable. So we're going to take our labels. I won't wiggle the mouse around to show you. Take our labels. We're going to rearrange them so that we can have them keyed by node, and then join with the nodes relation. This is we want to take for each node the labels and the comment identifiers, and send them along each of the edges in the nodes relation. Great. So we sort of need to do that, basically. It's not too much of a choice. We've got to rearrange things. We have now a join with a nodes relation, which allows us to produce essentially the same data that was at each node, but now at those folks who are one hop away from nodes. And we can, maybe this is an interesting point just to show off the join map operator, which allows us to write down what we want to do with each of these arguments that come in here. So we're going to write a closure essentially that's going to produce an output tuple. That closure gets to see the key, which is node. It gets to see the values for the first input and the values for the second input, which were label and comment for the first input. It's just the values associated here, and the value associated with the second output. And then we write down whatever we want to do here. Probably des.clone. Sorry, we're just looking at this line down here. Des.clone, comma, comment.clone, label.clone. And then we get to skip the map. Now, why is this worth doing? It's not so exciting in this case, but if these were, for example, strings, the default implementation of join just does all these clones, and it would have produced a cloned node for us, and we don't need that. So no reason to actually do that work. If we only wanted, for example, to produce the label as an output, we could skip all this other work in here too. There's even more advanced sort of lower level join implementations that would allow us to provide an iterator here, for example. So if we wanted to filter the results, we wouldn't even clone these things in the first place. It could be pretty sweet. All right. We did this so that we could semi-join by likes. This allows us to throw away the messages, essentially, proposals to new neighbor nodes that correspond to comments that that neighbor node didn't even like. So good. We want to throw those away. Though, we can get rid of it if we want, and I'll explain a cute trick that we can do. It's a moment where we sort of break from the relational paradigm. We can determine if that's a thing we like doing, but I'll at least explain what's going on. Having restricted all of these, we now concatenate in the initial proposals, right? We've gone one step out, but you should also be able to use your initial values if you want, your initial labels if you want. And then we run through and we just say, yeah, great, push the lowest, for each key, for each node and comment pair, push the label that is smallest. Remember, again, these are sorted. And then we do a little bit of work just to reorder the DLEs by node. By the flat triple that we had. They will be they will be ordered by node and comment, which isn't helpful. We could pick something other than this triple structure for iteration. We could get rid of one of these two maps if we wanted to just tidy things up. Maybe that's good. So let's for example tidy this up just a little bit here. We will have it be grouped by how do we want to do this? By node and comment, let's say, the label there, which will allow us to we'll have nodes comments here with a label dangling off of it. We still need to restructure them because then we want to join by node, not by node and comment. But the outputs reduce, and we should just be able to get rid of it, I think. So this will go around and maintain collections that are pairs of a pair of user and comment with a label, which means that we're going to need to tidy this up too, but that's fine. That's just acknowledging that the input is structured slightly differently. Great. We have the same trick that we might want to do here, where we fuse the count and join with arrangements. So counts data comes out arranged. We're going to manipulate it a little bit and then do a join, but we could just go ahead and do the join and see what we get as an output. To be honest, probably what this is telling us actually is, I guess there's an easier way to do this that isn't. We could just do the count, do the join, and then since this is a one-to-one, anyhow, sorry, we'll leave this. Leave this here. Basically, I'm thinking that there's a way to take the count in the map and put it after the join, essentially. But let's worry about that later, or not at all. Does this still build? Probably not, right? Yeah, no, definitely not. So what's going on? Cannot find value comment 414. Yeah, okay, com. Classic mistake. And 433, we expected. Okay, right. So since I was explicit about the type up here, submission, we need to. We need to fix that type. But having done that, we are good. So 360, we got rid of a bunch of, we got a bunch of consolidates, so we don't really need to talk about consolidate anymore. And whatever 422 was, now probably 421. Yeah, where we had previously said, throw away the node in the next operation, we at least just need to accept that it doesn't interest us here. Great. All right, so this looks like it compiles. Just clean up a few more of these things. I'm going to leave in the semi-join. So the cute trick that we can do, if we want, just to tell you what it is, the semi-join is there to make sure that we only bother to produce output for those people who actually liked the comment in question. This is a bunch of work to do that. There's a simpler way, which is, since we're concatenating in a proposal, which is that if you liked a thing, you should propose your own name, we could, in our reduce, say, only produce output if input contains key. Right, so we grouped by, well, I guess key dot 0. So we have a bunch of labels that have come in, and we should only produce output if one of those labels is ourself, basically. So we look at the key and say, well, we're the user such and such, key.0. There better be a proposal for key.0 in our input. And if there is, so this involves scanning through everything, but that's essentially fine. We already did enough work reassembling the thing. So this lets us skip the semi-join and just say if input input.iter.any of user com wget wait user equals key.0. Is that right? No, sorry. This is just label, I guess. Label equals. So this is, let's see if this compiles. Nope, does not. So I've gotten some refs totally wrong. This label wants to be derefed at least once, possibly 5 times. So it's still a ref to a thing. Let's fix that. And we don't care about weight, so we should acknowledge that. All right. So all that we're doing here is we're saying, just make sure that we are able to see ourselves in here. We could actually, since these things are sorted, we could even do a binary search if we wanted to. We could be really, really smart. But I happen to know that under the covers, we've already done a linear amount of work in the size of input to assemble input to show you. That's a far future differential to-do item. But yeah. So now we've done one fewer semi-join. We've fed all of our data through one fewer complicated stateful operator, and instead just threw another little bit of logic into the innards of our reduce operation. We've definitely, at this point, broken from a relational model where we, this reduce is not a top k or anything. Like it would have been a top 1, right? Like just produce the smallest thing. Great, that's a kind of relational-ish operator we could think about. This is now just a hunk of code that I wrote that does crazy stuff. But hopefully it's still correct. We can test it. A little worried that if it's not correct when we test it, we will not have the energy to debug it. It takes a little while to build, unfortunately. It was taking about 3 minutes before, even with just like white space changes in 3 minutes. So this is not a friendly computation. One of the problems, I would say, with differential data flow at the moment is as you build more and more interesting computations, each of these is a new thing that differential data flow Rust has to go and compile, and Rust more or less produces this massive amount of code that it hands to LLVM and says, good luck. And then LLVM has to grind through a gigabyte or so of intermediate representation and discover, like, okay, no, a lot of these are the same, or this isn't really that complicated. But one of the appealing things about a slightly higher level bit of code is, so when you use something like SQL, for example, your database doesn't necessarily recompile a from-scratch computation to run your query. It uses pre-existing parts, so pre-existing select operator, pre-existing join operator, things like that, which means your query can start running right away, which is cool. And you can do the same thing with differential data flow, and in fact, that's one of the things that we're doing at Materialize is exactly that. I'll ideally tell you about that more in the near future. For sure, you are meant to be able, for example, to write all of these queries in something that compiles in a fraction of a second, let's say, or it doesn't even need a recompilation. And then the performance is probably going to be slower, but it's a trade-off. How are we doing compile? Okay, we're still compiling. Cool. Oh, shit. Sorry. Quick interruption. There's an important thing that I forgot to change from before. Way back when, we have these environment variables that our test harness would set for us when we were running. That's great. One of them is sequences, which is how many changes do we want to apply. And I said, oh, make the default be 0 if we can't find it. No, it should be 20, which is the number of change files we have if we want to be able to run this ourselves outside of the test harness. Sorry about that. Yeah, this is all a lot tidier now, I think. Clearly, there are some things that we could, create some extend implementation so that we could feed an iterator directly to an input that would sort of collapse all these down to just 5 lines. A bunch of these operations, they're a bit noisy at the moment. We could try to make them a little less noisy. That's same. We've seen a few places, for example, in here where this is a mouthful. It turns out there's a helpful function that exists on cursors. So we can get a cursor here, and then cursor has a toVec method that will essentially dump the contents for us. It dumps them still in a differential representation, so as pluses and minuses with timestamps. But we wouldn't have to walk through the cursor and do all this stuff. We just have a vec containing keys and values and timestamps and integer diffs. But let's not do that right now. Let's let everything compile properly. We've got our gorgeous queries now written down, which are a pile of explicitly stated assumptions that are in principle now reusable if we wanted to go and make submissions be strings again, persons be strings again, dates be, I don't know. And same thing with our where logic. So this is almost certainly longer. I forget how long it was before, but almost certainly longer than before, but maybe a bit more reusable and more clear, I hope. While this is going on, let's drop over into differential dataflow. And I want to show you the sort of thing I was talking about with respect to the count producing arranged data. So if we go find fun count, here is fun count. And here's the implementation of fun count. Fun count, so it's from a collection of keys in some graph G with nice monoid type R. The logic says, okay, well, you should arrange yourself by yourself. Here's the key. We're just trying to count you. So arrange by yourself. Then we fire up this reduce abelian method. Oh, right, okay. All this is really saying is that we should go through and for each key pick out the accumulated value. That happens to be what's going on here. The accumulated value with count 1. So if there were 37 of a thing, we'll produce 37, the value 37 once. And this is great. This is now actually the output here, at this moment in the graph, right before the next method. This is an arrangement. This is something keyed by the type k, with a value type that is the count. And it's actually sort of pre-ready to go with any operator that wants its data arranged by that key, particular join on the key. Now, to make this ergonomic for other people, we actually reduce it down to a collection at the end. And that is nice of us if you're looking for a collection, but a bit too bad if actually you wanted the inner thing. So what we can do though is we can essentially just copy paste this hunk of code and say we're going to do our own count that returns an arrangement rather than the count that also then sort of destroys the arrangement and reduces it down to these elemental, like a stream of tuples. So that's what I was talking about when I was saying we could fuse count, which which produces arrangements, with join, which is able to start from arrangements. All right. From the sounds of my fan, I believe we have finished compiling. Excellent. Let's check to make sure. Great, we haven't screwed anything up. So we can do cargo run release projects models. Let's do a small one so that we don't stay here forever. Okay, this is definitely wrong. Or at least there's only supposed to be 3 elements in this list. So we've screwed a thing up. Though we went quite fast screwing it up. Let's see if we can figure out how we screwed up what I believe is our limit method, which did not seem to correctly. Yeah, okay. So this final grouping here, we had a take limit. We forgot about it down here. Forget who knows, but certainly didn't have it. So we make a small change to our program. Let's recompile it and see how long that takes. I have a sense, so we're going to go back and look at these pictures while that runs. This is now the join method, and I want to show you. Join is a trait. It is defined on a few different things. It is defined if we look for the impl region here. Join is implemented for collections. That's cool. We can do join map, semi-join, anti-join, a few cool things like that. But join is also implemented for the arranged type. So if your arrangement has the right structure, in particular, it's keyed by the key you're planning on using for your join, we have an implementation that is more efficient. Basically, it does not need to perform one of the arrangements that join performs. So join is going to say, you're giving me some streams of data, I don't know what these are. Step 1 is I need to shuffle all the data, and I need to build up some maintained indices, stuff like that. And that's what arrange is doing here. We can just skip that if the data are already arranged. So we see that we're still doing an arrangement. This is for the other argument, though. So the other argument's coming in. We do need to put that in the right form. But we're just directly calling into join core. Here, join core happens to be a trait. This is sort of the lowest level join that we've got going on. It takes 2 arrangements, and a result selector method that produces an iterator over output tuples. And basically, this is where we program what the join is going to do for each of our for each of the matches, basically between keys and the two inputs. And we can see there is a join core implementation for arranged. That's great. That lets us bypass the work of arrangement if our data are already set up properly. How are we doing here? So probably what I'll do is I'll make a copy, once this is up and running and looking a bit more correct, I'll make a copy of the directory. We can go through and we can look and see if we fuse the count and the join together, does that have any performance impact? Might not. Ideally, it's a little bit better. There's no reason that it should be slower. We're doing strictly less work. But, it's a mystery. Not always do you, by fixing some, elegant sorts of things to fix, you may not actually have a massive performance improvement. It'd be nice if it was, though. So if we look at the code here, that's essentially going to live. Where we said count here, you recall there was a little bit of arranging that went on, and then a reduce abelian, because abelian groups, some group theory here for those of you who like that. And then we'll skip the map. We won't do the map because reduce abelian comes out with an arrangement. We'll go directly into join. We could just do join, to be honest. We could do join map. We could do join core. Join map is probably sufficient, though, because join map is implemented for arrangements, so we'll still be bypassing the arranging step. Join core is mostly necessary if your second argument is an arrangement, because Rust does not do dynamic dispatch on other arguments, so there can only be one method called join map for any particular type. You can't have two different implementations depending on the type of the argument that's passed in there. That's fine. Sweet, all right, this ran. We could validate the output. We could just sort of eyeball it too. No idea. Let's just leave it how it is, though, to be honest. So where are we? I'm going to bounce up just a bit. CP differential to differential new. Right? All right. So we've sort of frozen differential new in time, but we can get back to work over here. Let's steal that bit of reduced logic that we had, arrange by self, reduce abelian. Throw that in here. Gross. And we'll do join map so that we can do the subtraction. All right. Join map, we still need to manipulate the post argument, but now we have a key, which is a post, which we might actually want, a count and a timestamp. Yeah, we're going to want all of these. And we want it to produce post count -1 timestamp. So that is, we can put these on 2 lines just to make it a bit more clear, if that's more clear. This is going to do our subtraction for us in place rather than doing it immediately after the count, which is meant to sort of at this boundary here between the reduce abelian and the join save us some data manipulation. Now we got to figure out what default val trace is. I don't know if you recall, but when we had a default trace before, it was actually this ord key trace. Ord key spine. So let's track down what default key trace was. Here it is basically the same thing, but with key instead of val. Differential data flow has two different data flow. Sorry, two different ways you might think of arranging data. The key type yes, okay, or val, spine. Yeah, but by key and by key value. So by key is essentially saying, I'm a key and I don't have any value. Think of it as the empty tuple, but I don't have a value. And key val says, yeah, I'm a key, I might have multiple values. You represent these a little differently because if you know that you're not going to have any values, don't even keep the space around to talk about those values. But the reduce abelian operator does need to know, hey, I'm producing an output trace for you. What do you want me to use? So we can't have default trait parameters here, unfortunately. So we have to explicitly say, yeah, okay, this word val is fine. Let's see if this builds. Nope. What did I forget? Probably some semicolons and crap like that. Yeah, so here's a semicolon. Oh dear. All right. Oh, this isn't so bad. Reduce abelian is kind of hidden to make sure that randoms don't just wander in and start using it. So there's this reduce core method, and we need to actually grab it specifically. Join map takes two parameters, but one was specified. Did I not successfully deparenthesize? Yeah, I got the parens wrong. All right. Put a comment there. That probably doesn't make any sense with a comment, but whoa. All right. What have we? Okay, sorry. This is my bad. So the closure for join map. These arguments we're getting in are references. As I mentioned before, it does not clone them for us in case we do not actually need to clone them. So for example, we happen to know count is an integer, just locally. So we can do count -1, clone, and now we are actually outproducing owned types, not references, and that should make us a bit happier. We don't need count anymore. I'm not going to fix that yet because we might need to comment that back in if the world blows up. But let's do the same thing in query 2. This is at the bottom here with the comments. So we did a count, did an explode, oh, to square everything, that's true. We did our count with the map right there. And our join is right below it. So we're going to make our com scores. This way, we're supposed to join in, though, this relation. Get that here. But I think things are otherwise fine. Let's see. No. Okay, we need to put in some using statements. We need to go find reduce core again. Great. Yeah. All right. Now let's get two windows open here. CD project, DT solutions, differential, new. All right. I was hoping this was already going to have been built, but I guess when we did the copy, it updated all the timestamps, maybe. And here we are in the differential directory, which is where we just made all these changes. And what I'm hoping to do is build both of these in release mode and see that one of them is different from the other. cargo build, release. So we've got two of these running at the same time. I'm sure that's tragic. And each of them is happily consuming as many cores as exist in the world. And let's see. Ooh, this is, by the way, the keyboard that I'm hoping will be arriving on Monday. I will be in Amsterdam and not able to use it. Yeah, so here's 3 instances of Rust. See? Oh, okay. Exhausting. Anyway, so this is the sort of clever thing that differential dataflow enables us. Since we have a restricted computational model, this one where we turn on a fixed set of workers, we partition the work between those workers in a way that we're actually able to share some of the in-memory state between different dataflow operators, in this case between the output of the counting action and the input to the joining action. And this is great. This is, in a different system like a Spark or a Flink. As far as I'm aware, unless they tell me otherwise, this is a boundary. These operator boundaries are places where they would want to need to ship data to other machines, unless they were able to synthesize a more interesting composite operator that simultaneously does a count and a join together, which is totally possible. They could, in principle, be doing that. It's a smart thing to do. It's not something we do because we aren't doing our own code gen. But in a sense, there's the principle that we're observing is that for a few operations in a row, we're arranging all the data by this particular key, and we're doing a sequence of things on it now: the counting, the joining, the subtracting by 1, and we don't need to exchange the data or even re-index it between these boundaries. So there's a little block of code that's all done by key with the same key, and it's good that we do not need to redo that work. The other thing that's cool about arrangements, we saw this a little bit with when we looked at our outputs, but it wasn't really showing off the coolness, is that arrangement that moves from here to here, we could totally capture that trace. Remember there's this trace field? We can capture that, and we can lift that out of our computation, and our worker can just hold on to that. And it will develop and grow as the computation proceeds. But it can then use this trace in a subsequent computation to seed the computation. It's now able to be used as an input in a totally unrelated dataflow computation. I mean, it'll be related because that data itself derived from some other computation, but they don't have to be in the same dataflow. They don't have to be defined at the same time. So we could, for example, take our inputs, our comments, our posts, things that have keys, and comments and posts have keys, likes. No, there's no key here because many people, it's a many-to-many relationship. But we could arrange the data by the submission. So each time we need to join with comms using the submission data, maybe we're looking up the date or we're doing some other things. We have that data prearranged. We maintain it only once throughout the entire computation, even if both queries 1 and 2 need comms and posts indexed by their ID. I don't think they do. So I don't think, for example, we ever index comms by its index other than in query 2 when we look up the date time for a particular comment. And likewise, I don't think we use posts indexed by their identifier other than in query 1 where we here look up their date time by the post identifier. So, that would be cool, but it's not strictly necessary here. It's the sort of thing that if we did it, then our host program, sort of main.rs, would incur the cost of building and maintaining comms and posts. And when someone actually wants to show up and deploy query 1, the incremental cost would be a lot smaller because we wouldn't need to go and reprocess at that point comms and posts. We just need to pick up likes or no's or stuff like that. So, they're running. Yep. Yeah, it takes a while to compile differential data flow. It takes a while to compile Rust code generally, and it takes a while to compile differential data flow because it has a fairly heavy reliance on generic programming. So your map operations are generic closures that get nicely inlined instead of having a function we call for each record. Nicely inlined does mean that there's a lot of code gen for each of these maps that have totally unrelated implementations because they're totally different. And they're not very similar, but all right. This one was started earlier, but had a little bit more work to do. Let's see. So the sorts of things we're going to run are cargo run release. Isn't both of them. There may be no appreciable difference. So we're going to look at things like timestamps and try to eyeball how long did various things take, but it might not actually amount to anything. But we will know that we are better people for having optimized that rearrangement. So let's run this. Great. I'm just going to run it twice to make sure we didn't have any data loading. Since the times are pretty small. All right. You might notice that we flip back and forth between the two. Same output. Pretty sweet. Though, to be honest, it looks like the output's actually static all the way down. That's probably wrong. We should look into that. But let's take a peek at, so this is the old version, this is the new version. If we just look at some of these times, we can see a few interesting changes, I think interesting changes, in the update times. So the initial time here, not too different, right? Like, we shaved off 7 milliseconds or something like that. It's not super exciting, out of 1.5 seconds. But if we look at, generally speaking, if we look at these update times, which are, just below a millisecond here, and then swing over to here, they're now noticeably more than a millisecond. And I'm just flipping between the two things, and largely, okay, this is a pain in the butt because they're not totally ordered. The old version is a little bit faster. So for example, here versus here, just over a second. Here, quite over a second. All right, there are no conclusions we can draw, I think, from this, except that probably the output's wrong. I'm just weirded out by the fact that the output never changes, which I don't think is right, unless we've somehow screwed up and not actually input any data. Let's see. I am slightly disinclined to actually go and try to debug the correctness stuff on this. We went through this before in the first post, just the debugging process. Mostly it just takes so long to compile that diagnosing what's going wrong in the output at this point is a bit more frustrating. Let's run it on a smaller input. Okay, so this one's output changes. I wonder if we can check the outputs and see if we're expecting for 128 it to change a lot, maybe never. Models, 128. Oh no, sorry, expected results. So for a scale 128, yeah, we do expect it to change after the 10th iteration. Is there any relationship, by the way, between these results? I mean, these are just wrong. 67, 83. Doesn't look like we've got any of these right. I wonder if we screwed up. So we had some places where we just casually typed in, copied and pasted some things, and maybe didn't think hard enough about exactly which of these we were capturing and were we taking the right ones. We are reversing our iterators each time, which is, I think, the right thing to do. But, yeah. My energy for fixing this is quite low. You know, this optimization might be forgetting something. Nothing leaps to mind, but also, this is for sure, you know, one of the pain points with differential data flow is that diving in and throwing in some, you know, few invariants here or there involves a recompilation loop, which is just annoying. Yeah. I don't know. Let's see how long this thing takes for a debug build. And if it's not so bad, then we can try to fix this using debug, using some smaller test sizes. But neither of these were right. Yeah. So this does not appear to have been related to fusing the counts. It's just something else something else entirely. Oh, well, hold on. Sorry. Wait. I mean, maybe yes, but oh no, we're fine. Okay, sorry. I was looking at the Q1's updates, which do change, but since we're outside of the test harness, it runs Q2 and Q2 only, which means this. I don't know that we're fine. Sorry, but what we should be seeing is blah 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 81, 43, and 07. And what we saw was 81, 43, 07. Okay, so this is possibly actually totally correct. Let's wander over to the benchmarking harness, add in, which is in reporting, I think. Nope. Output. .cs. Nope. I don't know. Is it reporting? There's some JSON thing somewhere that we have to figure out where to. Oh, why is this? Why am I results? Scripts. Where did that stupid JSON thing live that told us which? It's like a maybe it's config. Yeah. Okay. Reporting.json. It wasn't this one. It's the other one. Wherein we can specify. So we're going to do differential if we do also differential new. Get that. Let me just make all these make a bit more sense, because right now I think differential new points at differential. What we should probably do new, and we can copy over differential new 08 to just differential 08, and then repair it. So it will now be the 8-threaded version of. Oh no! Oh, crud! Jesus, I'm on my laptop. We don't have 8 threads. Let's just do these folks here. So I have no idea how long this will take. Scripts 5. So single-threaded up to 512 sized things could be bad news. I'm not entirely sure. Oh, I am delighted that there were no errors. This will show us that there are probably lots of errors, but I'm super happy that there weren't. One thing that weirded me out a little bit, and I don't know how we don't have any of these outputs around anymore. There are some places where we take, let's say, a quarter of a millisecond, 250 microseconds, which doesn't sound like a very long time. But when you look at the file that we are processing, so I wonder, 128 may have had some of these, maybe not. I really don't want to. This is so gross. I don't want to look at any of those other filthy files. If we look at these folks here, oh, none of them have. So for some of the sizes, they're just some empty changes. The file is literally empty. So nothing has changed. Maybe we have some in 1024. I feel like I saw some there. These are all just in a straight line too. Ah, great. So change 09, yeah, just empty. It's got nothing going on, but it still takes 250 microseconds. And change 4, it's also empty. So there's a legit question is why does it take a few hundred microseconds to do nothing? And there's some legit reasons, like workers need to confirm amongst themselves that no one had anything that they were looking at. But it still seems like a lot of time, and maybe it has to do with the fact that we have to actually go out to the file system, open up the file, confirm that it is in fact empty, which maybe involves a little bit of kernel blocking and stuff like that. But that's the thing that would be great to try to lean out. One of the things that it could be is that we are, as we're running through all these changes, that's where we're actually grabbing the files and opening them up and reading all of them. We could totally do that ahead of time. What the hell is this? Yeah, I have no clue which file this is. It's not all of them, but let's just ignore it for the moment. Once this gets running, we're going to have to Control-C and then start it again, just to make sure that, I've randomly been scrolling around and crap like that, and that's no good. So, what was I talking about? Oh yeah, so we could, in principle, preload all of these change sets. It's not entirely clear if that's kosher with respect to the benchmark. They imply that you should feel welcome to preload, for example, the main body of the data. And it's good to think through. Okay, what if we didn't store our data in plain text? What if we actually had more structured storage? So the data were more or less ready and typed in memory representations ready to go. Would we potentially avoid going and having a chat with the file system if we already had the data at hand? Legit thing to think about and measure. For those of you not aware, the laptop is getting on 5 years old at this point. Super powerful laptop, still goes really fast on graph processing. Does not compile Rust code quite as fast as graph processing. It's kind of embarrassing actually for like a lot of the computations I work with. Compiling the binary takes an order of magnitude longer than actually doing the data analysis itself. So if you want to point yourself at the 1.4 billion edge Twitter data set and then do connected components on it using union find Hilbert get great, it takes 5 seconds, 6 seconds. If you want to compile like this sort of program, it took what was like 7 minutes before. Which should give you some calibration on if you're trying to support people doing ad hoc analytics. Compiled code is really cool, but it's dog slow at the moment, the compilation process. And I'd be delighted if more effort gets put into that. I don't think the right person to do it. But all right, we started to run. Let me just kill that so that we can start it cleanly. And this will take a little bit of time. And it takes a lot of time. I will just fast forward through all of this. I'm going to go get a drink. Well, I'm back. As you can see, things are entirely wrong. Wrong. Problem is that we printed out the vector containing 3 things, and it wanted to see pipes in between things instead of the vector itself. So that's catastrophe. It's a real pity. Yeah, we're just looking at all these things. These are the right answers. They're just printed badly. So let's tidy that up. I'll have fast forwarded all of this for you, and then go get a sandwich too, maybe. Let's fix it up in both places. Oh, this is gonna be gross. Well, we could just make this return a string, and we could do it at the end. Here. This is probably the easiest way to bandage this up, though, as opposed to hitting each of the 6 places we print out strings and writing all of them in there. So right before we go and arrange by self, we can dot map vec to format ta-da, pipe ta-da, pipe ta-da, vec, oops, vec 0, vec 1, vec 2, and then the same thing query 1. Ooh, believe that compiles, doesn't implement display. Yeah, that's a good point. All right. We'll just assert that it should. String does, so bit for us. This is a submission, so we just need to plus that into our assumptions. Same thing over here. Oh, and sorry, we want to do the same change for differential new. Ooh, sorry, I just opened that up as a project. That's a bit crazy. What am I doing? Deleting lines. I don't want to do that. No, I don't. Oh, good lord. Go away. Go away. Go away. So annoying. Oh, for fuck's sake. This is why I don't load extensions, right? They decide that you really want to be their best friend, and I really don't. String, and then we do that same change here where we drop in a we don't drop it in because we didn't keep it in our buffer. Soup. It's com score, we should fix that. And we need to add the display constraint. Stud funct display. Yeah, probably works, right? Who knows? Actually, if before I wander away, let's cargo check, just to be clear, see projects, AT, solutions, differential new, check. All these things are here so that we can not use chrono. Sorry, that's not fair. We are using chrono to turn a date into a nanosecond. And yep. All right. So this is good. We got early warning about something code is blown up. Differential new. Somewhere we forgot to change the output type to be a string. So we got string there. We screwed this up and didn't put string here. Great. So let's start this running again. This will take a little bit of time. I will try to either edit this out or fast forward for you. And having had my drink, I'll now go get a sandwich. Ooh, I'm back. It's done. I don't know how long it took, but I had a delicious sandwich. Let's open up diagrams. Diagrams. All right. So, what did we plot? All right. We've seen a bunch of these things before. Differential old is crep. Differential new and differential are basically the same. This is, we had that clever arrangement trick. Let's see if they're in any way different anywhere. Hard to say. Let's look at Q2 again. Not obviously meaningfully improved. Yep. So let's call it approximately no difference. Though, ooh, so excited. Approximately no difference, though. We know in our hearts that we did a better thing. Yeah, who knows? And we still have the right answers. So, great. I'm gonna call it there. I think there are a few more cool things to do potentially, but I just figure it's a good time to stop and let you all do your own thing too. I was tempted to take these 20 updates and show you what it looks like when you batch them up, and instead of doing a sequence of 20 updates, you put the timestamps on there, so you distinguish each of those batches of updates, but then you maybe process them in groups. Maybe you take updates 1 and 2 at the same batch with timestamps 1 and 2 stamped onto them, but do them together, and the throughput increases. I've already checked this out. The throughput increases, and although the time to very first result goes up, the time to just about every result thereafter goes down, because you don't waste all that time doing 1, then 2, then 3, sort of leap immediately to 1, 2, 3. And then all of the 4s, 5s, and 6s are faster from that point on. But let's do that at a different time. We'll just stop this for now.